So first of all, let's sort of like recontextualize all this. So yesterday we saw a particular type of chaotic system, which is chaos in dissipative systems. So a dissipative system, you remember, is one that's able to dissipate energy, to lose energy through friction, basically. And today we're going to look at perhaps what was one of the original applications of chaos theory, but which was actually in non-dissipative systems, namely mostly in the field of astronomy. Because basically stars move around in a vacuum, or at least space is very, very close to being a vacuum. So there's no friction, right? If a star is orbiting around the sun, if a star is orbiting around another star, a planet around the sun, well, that orbit, if it's periodic, it is going to remain periodic eternally. It's never going to spiral in as a damped oscillator would. So basically the thing today is that I'm going to start with a few preliminary remarks, just kind of like broadly sketching the sort of like curiosity, the oddity basically of applying chaos to Hamiltonian systems and astrophysical systems in particular. And then we'll move on to the meat of the subject, which is really, well, what we mean by Hamiltonian systems, how we solve them, basically, and then a few applications from a wide variety of different fields in astrophysics. Okay, so some preliminary remarks. Basically, astronomy, so the field of the study of stars, of stellar objects, of celestial bodies, was always kind of associated with a degree of perfection, right? Planets have completely predictable orbits, the stars are kind of fixed in the sky. Everything in astronomy seems to be constant and predictable, right? And so this is an example from Julius Caesar by Shakespeare. At some point, Julius Caesar is, I think Calpurnia wants to warn him about the Ides of March and to change his decision about I think the punishment of some other centaur. And basically Caesar answers, I could be well moved if I were as you. If I could pray to move, prayers would move me, but I am constant as the northern star. Now, so the funny thing about this is that the northern star isn't actually constant at all, right? It's a variable. So the constant, Polaris, the North Star, is actually what's known as a Cepheid variable. So it's actually a star whose luminosity varies actually quite rapidly over the course of a few days, right? So this here is the luminosity of the star, and this is, these are different dates, right? So this gap, that's just a bunch of, I think they just weren't observing that day. But as you can see, Polaris is not in fact constant at all, not at least in its luminosity, and also even in its position in the sky. Actually, there's something known as the precession of the equinoxes, which means that Polaris is the North Star only now, but it won't be in a few 100,000 years, basically. So, essentially, yeah, the prejudice was astronomy is the field of perfect things, of things that move in sort of like perfect circles, that always repeat themselves with perfect predictability. And it turned out pretty early on in the study of dynamical systems in the 19th century that was actually not the case. Okay, so a quick recap of the chaos in dissipative systems, because this is really what we'll be contrasting with, right, in the study of Hamiltonian dynamics. So first of all, as you recall, in a dissipative system, the attractor of the system had this weird geometry. It was a strange attractor, which essentially meant that when you had nearby orbits, they would sort of diverge because the attractor had a very unpredictable orbits. So that was translating this notion of sensitive dependence on initial conditions that has been one of the motifs, right, of chaos. But also the strange attractor had this sort of swirling pattern, right, but always did seem to fold back in on itself, which allows for the second property of chaotic systems, which is recurrence, right? They don't actually, the uncertainty, the difference between two orbits doesn't grow without bounds. Eventually they will come back arbitrarily close to each other, right? So these two seemingly contradictory properties, recurrence and sensitive dependence, these were the reasons that we sought out a new kind of geometry to model those strange attractors. And what we did was we came up with, the notion of a fractal. So a fractal being something that can be bounded in a finite area or in a finite volume, but have infinite complexity, right? Have features that can kind of keep repeating themselves over smaller and smaller scales, so that eventually you can fit in a completely chaotic orbit within actually a finite volume in phase space. So, for these reasons, basically, in a Hamiltonian system, you can't actually have an attractor like this, because the folding and stretching in the dissipative systems was really due to friction, right? To the fact that the system was able to lose energy. And so you had this kind of like stretching and squeezing of orbits. This isn't actually possible in the Hamiltonian system. In a Hamiltonian system, energy is constant, it cannot be dissipated. So Hamiltonian systems can display chaos, but their route to chaos is going to be slightly different. Okay, so today what we're going to be doing is, first thing, just quick recap of the sort of original problem of chaotic dynamics, which was the three-body problem, right? As you recall, it was tackled in the 19th century by Poincaré, amongst others. It was the first instance of classical mechanics bumping up against the problem of unpredictable, nonlinear, chaotic motion. The second thing we're going to do is basically introduce the notion of resonance. So resonance, as we're going to see, is actually the way that a Hamiltonian system can become chaotic, right? So resonance is something that you will probably have some kind of intuitive understanding of, so we'll really kind of lean on that heavily to then apply this to systems you'll be less familiar with, such as the solar system and astroseismology. Okay, in the third part, what we're going to do is really study the orbits of stars in galaxies. In particular, you'll see that some orbits in galaxies can be very regular, right? Kind of the same way that you have in the solar system with neat elliptical orbits or orbits that generally have a sort of like regular pattern to them. And some of these orbits will be chaotic, right? And we'll see how the transition between these two things occurs, right? In particular, we'll see how that links back to resonance, and we'll find that the sort of spatial organization, right, the organization of chaotic versus periodic orbits in phase space will look actually quite a lot like the problems we saw for dissipative systems, right? Where, as you recall, in the logistic map, there was always this thing with the, if you looked at the parameter space, right, so if we go back to our logistic map, there you go. So as you recall with the logistic map, you had this thing where chaos started to occur after a few period doublings, but actually there are always patches of regular motion, right, interspersed between the chaotic bits. And we'll find that actually something very similar happens in Hamiltonian systems, right, where essentially you have chaos appearing at certain, you'll have chaos appearing in certain bits of the phase space, but it'll always be interspersed with areas of order. Okay. So, first thing, chaos in the three-body problem. So this is something that we've seen before, right? So this guy over there is the French mathematician, Poincaré, and he was the first to try and answer the question, are there analytical solutions to the three-body problem? That was a problem, I think, that was proposed by the Royal Academy of Sweden or Norway, some Scandinavian country. And instead of solving the problem, basically what Poincaré did was he sent his submission essay, and he said, well, essentially the problem can't be solved, right? Actually, this isn't a problem where you can find neat, regular solutions, except in very particular cases. And so basically, you can see how that occurs in a fairly straightforward way, just by looking at simulations, right? So this here is a simulation of the three-body problem. You have three identical masses. You just have one type of interaction between them, right? They all sort of attract each other via gravitational forces. And there you go. So this is the motion of these three objects as they evolve with this very simple interaction, right? Each one of them obeying Newton's inverse square law. Oh, so the stuff that you can't see, the equipotential lines, don't worry about that, it's not really important. Okay, so as you can see, it's sort of fairly unpredictable motion, right? You can see that there are moments when you go back to something that looks like a two-body problem, but then the third one comes back in, and eventually this system is completely unstable, because as you'll notice, towards the end, one of the stars just gets kicked out, right? And the other two stars continue orbiting around each other. So this is something that really happens in galaxies, right, and in star clusters. Actually, because it's not unusual for stellar systems to have three stars orbiting each other. But the point is that this is quite often unstable, right? So you'll have two of the stars, usually the closer ones, will get closer and they'll just eject the third one. And this is something that genuinely happens in stellar systems such as globular clusters. and is actually pretty important to explain the stability of certain of these clusters. Okay, so this is an example you saw of chaotic dynamics, right? You had chaotic dynamics in the start, and then eventually what you have is an instability where the star gets kicked out. Hello. But the point is that the three-body problem is not actually chaotic all over its phase space. There are certain initial conditions where it will have actually regular solutions. So these regular solutions, they're not as neat and as simple as Kepler's ellipses, but they do exist. And I do want to sort of illustrate that with a few examples, again from simulations, where this is a three-body problem, but where we've picked special cases, special initial conditions, so special initial values of velocity and position, that actually allow for regular orbits, right? So periodic orbits. Although, as you'll see, the shape is not always obvious. So this is the first kind of regular orbit. So it's completely regular, right? It does repeat itself eternally, but it's got a kind of a funky shape. You get quite a few of these, right? There are a whole bunch of different families. Here I'll show you another one. So you see these two are forming a kind of rosette. Here, again, this is going to be looping back in on itself, but this time creating a fairly complicated shape. So anyway, you get the point, right? The point is that the two-body problem is chaotic in that it allows for chaotic solution, chaotic orbits, but it's not actually going to be chaotic all over its phase space. There exist initial conditions that will lead to regular motion, albeit regular but complicated. So this is like the first important thing, right? And the idea is that given that we know that for a given problem there will be regular and chaotic motion, we'll be wanting to give a more precise definition of what it is that we mean by regular motion and chaotic motion, right? So this is a general problem, right? So what we're looking at here is how you solve the dynamics of a Hamiltonian system. So a Hamiltonian system, as you recall, is just a regular type of dynamical system, except it doesn't dissipate any energy. So an example of Hamiltonian system that we already saw was a simple harmonic oscillator, right? So it's always a simple harmonic oscillator. It comes back every time. So the harmonic oscillator had two state variables, right? It had the displacement and it has the velocity of the oscillator. And as you recall, the particular structure of this simple harmonic oscillator in phase space was simply a circle. Oops. So what does this mean? Essentially, for the simple harmonic oscillator, the system was bound to a particular bit, to a particular subsection of phase space, namely any solution to the simple harmonic oscillator has to lie on a circle. So if this is for one type of initial condition, for instance we'll call this one x1, then you have another possible initial condition here, we'll call it x2, but it's still got the same structure, right? It's still a circle like that. And you recall the reason why these things were circles was that you could actually write down the total energy of the system, which is also known as Hamiltonian in this case. The total energy of the system was just the kinetic energy and the potential energy. And the potential energy for a simple harmonic oscillator was just 1/2 of kx squared. The kinetic energy that you will know is 1/2 of mv squared. So basically, this thing is the reason, this equation, right, the fact that the sum of the squares of these two variables has to equal a constant. So this is constant because energy can't be dissipated. The fact that these two sum to a constant translates in geometrical terms to the simple harmonic oscillator being confined to circles in phase space. So it can't actually go anywhere where it likes. It is really stuck to these particular circles. This is a very simple example, right? So this is a problem that has a two-dimensional phase space and has one integral of motion, so one constraint on where it can move in phase space. Which means that if you have a 2D phase space and one constraint, one integral of motion, then you reduce the dimension of the problem by 1. So instead of living in 2 dimensions, you actually only live in 1 dimension, right? The system can actually only explore a line. So this is what we mean by an integral of motion, right? An integral of motion is something that has a constant value during the evolution of the system, and that depends only on the system variables, v and x, and not on time. So as you can see here, so E is an integral of motion. And the idea is that to solve a Hamiltonian system, what this means is simply you reduce the dimension of the problem by finding enough integrals of motion, and then eventually you know where your system lives in phase space, right? And this is the broad idea. So for a 1D system, for a system like the simple harmonic oscillator, you have 2 dimensions in phase space. And if you find 1 integral of motion, it means that the system actually stays on the line, because the line is a 1D, because the line is just a 1D object, right? So we can already generalize that to slightly more complicated problems, right? Imagine instead of having a 1-dimensional harmonic oscillator, you have a 2-dimensional harmonic oscillator. So now, instead of just having the potential being 1/2 of kx squared, we now allow a slightly different problem. So the kinetic energy is still half of the velocity squared, but it has a velocity both in the x direction and the y direction now. So this is just a 2D simple harmonic oscillator. And the potential energy is 1/2 of k y squared and 1/2 of kx squared. So here, I've only added, well, let's call this k prime, so it's not the same as k. So the only thing I've done is that instead of having a simple harmonic oscillator in 1 dimension, so it oscillates like that, it can now oscillate in 2 dimensions, but with exactly the same dynamics, right? But now, instead of having a 2D phase space, well, we have a 4D phase space. So we have x, vx, y, and vy. So if we want to solve this problem, we now need new integrals of motion, right? We need to find new conserved quantities. As it turns out, these conserved quantities are pretty much the same as before, in that basically the total energy remains constant, but we'll also have other constants of motion, right? We will have Ex, which is just this part, the 1/2 of m Vx squared plus 1/2 of Kx squared. So that's still conserved. And Ey, which is just this bit with the y bit, is also going to be conserved. Okay, so what this means here is that now, instead of having 1 integral of motion, we have 3. But that's okay, because we need 3 integrals of motions, right? Because now we have a 4D phase space. So 4D because we have 4 variables. And we have 3 integrals of motion. Basically, to interpret what these integrals of motion are, you just imagine this pendulum, this oscillator, it completely decouples the motion in the x and y directions, right? So basically, it's as if you just superposed a simple harmonic oscillator in the x direction and a harmonic oscillator in the y direction. And as a result of that, individually, the energy along the x direction is conserved, and the energy along the y direction is conserved. So you now have Ex, and Ey, which are all integrals of motion. You have a 4D phase space, 3 integrals. Well, that's fine. The system stays on the line, basically. So you've solved the problem again, but this time it's not going to be a circle like that. It's actually going to be a closed loop like this. So essentially your system is confined on the surface of what's known as a torus, and on the surface of that torus, it actually doesn't follow the full 2D surface. It goes in 1 dimension, because it goes like that, but it loops back on itself. So this thing is still a line. You've still, you've still confined your system to a 1D, to a 1D structure in phase space, but your phase space is now 4-dimensional, right? Okay. So this is a special case, right? There are actually very few systems where you can find that many integrals of motion. These things are quite rare. Essentially, you have simple harmonic oscillators and the Kepler potential, right? So the potential of planets orbiting stars. Because basically what happens is that in the case of the harmonic potential, at least of this particular harmonic potential, where I have this two-dimensional harmonic potential, in this case, I loop back onto where I started in the phase space. However, in general, these kind of 2D potentials, if they have only two integrals of motions instead of three, what they'll do is they won't loop back in on themselves exactly. What they'll do is they'll come back here, and they'll do another round, but it'll be shifted slightly. And so if you wait long enough, instead of being confined to a line, it'll explore every bit of the surface of this torus in phase space, right? So this is the idea, is that when we have regular behavior in a system, it means that we have integrals of motion, right? You have things that keep the system confined to a subspace of the phase space, right? When it becomes non-integrable, so when you can't find any integrals of motion, that's when the system becomes chaotic, basically. Because what it means is that now the system still conserves energy, but your system is allowed to move around anywhere as long as it remains at a constant energy. So that's, if you have for instance, if you have a 4D phase space and only one integral, namely energy, then in that case, that means you can still move around in 3 dimensions, right? So your motion can still be extremely complicated and completely irregular. So this is what we mean by integrable versus non-integrable. Basically, integrable systems, they're the ones that we deal with in undergrad classes, right? They're the ones that behave nicely. You can write down exact solutions for them. Non-integrable systems, well, it's the same thing as with the nonlinear systems. They're tricky, right? Usually what we do is that we'll try to find some integrable system that approximates them, and then hope that by perturbing it a little bit, we can get away with not going to the chaotic stuff. Okay, so essentially it's the same procedure in physics as always, right? Is that once you've found an integrable system, well, you're just going to perturb it a little bit, because ultimately you know that in reality no system is going to be perfectly modeled by your kind of like very neat, perfect, simple harmonic oscillator, or your very neat, perfect Kepler model. You know that there are going to be, perturbations to these models. So if you want to think concretely about what that means, imagine, for instance, you've got your Kepler potential. So Kepler potential means you have one point at the center, the sun, for instance, and planets orbiting it. So in the first approximation, all the planets are just feeling the influence of the sun. But obviously, at some point, we're going to want to take into account the fact that there are other planets. And so we'll just start adding a first perturbation. We'll add the biggest planet. We'll say, okay, now we want the influence of the sun and of Jupiter. Then we can add Saturn, etc. And the question is, how does the phase space structure of our system change when we add new perturbations? So perturbations can mean two different things, basically. There's either what's known as time-dependent perturbation theory, which is where you add a potential that varies with time. So for instance, if I'm studying the influence on asteroids in the solar system, I'm studying the influence of the Sun-Jupiter system, right? So Jupiter I'm going to model the sun as being immovable at the center, but Jupiter is going to be coming around, once every 3 years or so. So this is a perturbation that has a time dependence. But I can also look at the time-independent perturbation theory, which is this case. So for instance, imagine you're looking at the Earth-Moon problem, right? So you're modeling the Earth as a perfect sphere, the Moon as a perfect sphere. This is just a simple two-body problem. You know how to solve this exactly. But here's the deal. You know that the Earth isn't actually spherical, right? It's not perfectly, yes, sorry. Yeah, exactly. So in time-dependent perturbation theory, your perturbation depends on time, right? So you have, for instance, you know that Jupiter just keeps swinging by every 3 years. So if you're an asteroid on one of the belts, then you only feel the influence of Jupiter, strongly every 3 years or so, right? So this is what we mean by time-dependent, is that the thing you're adding, the parameter you're adding, depends on time. Time-independent means that basically you're not adding something that varies with time, you're changing the shape of the potential, right? And it's maybe worth taking having a think about what that means for a system like the Earth-Moon system. So again, first you model the Earth as spherical, the Moon is spherical. It's a simple two-body problem. You know how to solve this. This is Kepler, right? This is just the Moon orbiting the Earth on a circular on a circular orbit. But this wouldn't actually explain a whole bunch of things we know to be the case with the moon, right? So for instance, we know that the moon is only ever showing us one side of its surface, right? So why would that be the case, right? If the system were as simple as two spherical objects rotating around each other, there would be absolutely no reason for that to be the case. The point is that neither the Earth nor the moon are completely spherical. They're all slightly oblate. So oblate just means you take a sphere, you squish it a little bit. And that's an oblate spheroid, right? And they're oblate because they spin on themselves, right? So as things spin on themselves, centrifugal force just kind of pushes things away, and so you get this kind of like a slightly squished shape. So the thing is that the potential, so the gravitational influence of a squished shape is not the same as the gravitational influence from a spherical shape. So what you'll do is that in your equations, you're going to take the spherical solution, because the spherical solution is nice and integrable, you know it, and you're going to add a little perturbation. So you'll say, well, I'm going to treat the squishing as a small extra perturbation that I'm adding on top of the system I know how to integrate. Now the point is that when you're doing this kind of perturbation theory, the squishing is permanent, right? There's no time variation. You're really just, you're changing the way the potential behaves. You're changing the way that the system interacts, right? But that dependence, well, that perturbation does not depend on time, right? So we'll see that these two types of perturbations, time-dependent, time-independent, will lead to some fairly different behavior, basically, in the systems that we'll be studying today. Okay, so this is actually an old example, but which is quite interesting. So, I don't know if you're aware, but epicycles, they were a trick invented by Ptolemy and Hipparchus to try and make the geocentric model work, right? So they believed that the planets were orbiting the Earth. The problem was, well, how do you explain the fact that clearly, the planets don't describe circular motion around the Earth? And so they came up with this idea that really they were circular motions, but that you had to superimpose another circle on the small circle, and that's essentially, if that didn't work, you could add another circle, and it was cogs within cogs, right? And that if you added enough of them, then you could more or less approximate the actual observable motion of planets in the sky. Obviously, this model was scrapped in favor of a much more simple one, namely the heliocentric model. But the funny thing is that epicycles are actually a very useful thing, right? So the way in which they were used by Ptolemy and Hipparchus was wrong. But actually, they're one of the first instances of perturbation theory, basically. They have because the ancient Greeks already had this intuition, right? That somehow, if you know that something is well behaved in a particular way, that you can just make the system a little bit more complex by adding another little motion on top of it. So here, what we're doing is we're back in the heliocentric model, where the sun is really at the center of the solar system. So Hipparchus and Ptolemy are wrong on that point. And now what we're going to do is we're going to try and model the orbit of the planet as a circle. So in reality, the orbits are ellipses, right? But what we're going to do is we're going to say, okay, well, let's assume that the planet lies on an orbit that is reasonably close to a circle, right? And it's true, right? The orbit of the Earth, for instance, doesn't have a huge eccentricity. So what happens is that what you do is you superimpose a little circling around on top of the initial orbital motion. So if the planet were just on a circular orbit, it would go on the dotted line here. And now what you do is you allow the planet to also move around this point along this little ellipse here. So this is an ellipse that has a 1/2 axis ratio, in that this is twice as large as this one. And as the system moves, basically, it not only moves around the sun, it moves around this point. So it orbits here around this point. So what you get here is, if you superimpose this motion and this motion, so the full line here and the dotted line here, you superimpose both of them, what you get is the dashed line here, which you can barely see because the dashed line is actually superimposed to this full line, which represents the orbit of a real planet, right? So basically what you're seeing is that epicycles manage to capture something almost as, they capture the motion of the planet almost as precisely as the original ellipse. So in this case, because we're in the Kepler system, with the sun is really a point mass and the planet is also a point mass, this ellipse has a curious property, which is that actually it takes exactly the same amount of time for the planet to orbit this point as it does to orbit the whole sun, which means that as you come back to this position, you're also, as you come back to the position on the dotted line here, you're also back on the same position on this line, which is why the orbit actually closes in on itself. So this is a particular case, kind of like with the simple harmonic oscillator, right? Where actually the orbit eventually does come back to its initial position, right? So it's a strictly periodic orbit. In reality, if you look, instead of looking at a sun-planet system, you say, well, this is now the center of the galaxy, and this is, the motion of a star around it. Well, this time, you can still use epicycles to model the trajectory, but this time it's not going to close back neatly, because basically you're going to do one circle around the galactic center, and as you return here, you're not actually going to be in the same position as you started out. So for instance, you will be back, I don't know, here for instance. So you're back to this point on the main circular orbit, but on the little elliptical orbit, the little epicycle, you're not back at your initial position. So instead of closing back in, what happens is that you go like this. So you start out here, you go around the circle, but instead of coming back to your initial position, you come back slightly away from it, so you go like this. Now you're back here, and you're going to describe what is known as a rosette, right? So in a potential that's slightly more complicated than the Kepler potential, you're just going to loop around like that. And you can see that this still contains very useful information, right? You're not confined to a line in space, but you are confined between these two extremes, right? You're never going to leave these two extremes, and this is still regular. Perfectly predictable motion, except that this is no longer periodic, this is quasi-periodic, because it never quite repeats itself. So, what is the point here? The point here is that you can model the influence of a perturbing potential, of a time-dependent perturbation, as being just something that you superimpose onto a known simple solution. So basically, you have, if this time, for instance, you wanted to model the influence on the planet of Jupiter, right? So what you do is that you take this solution, the circular solution, and you're going to see how the presence of Jupiter, for instance, might affect how the planet moves around its epicycle, right? So epicycles, really what they look like is kind of like simple harmonic motion, right? Basically, your planet is sort of oscillating on its on its major and minor axis. It has these epicycle frequencies, which are kind of analogous to the frequencies of the simple harmonic oscillator. And what we'll see is that if you happen to perturb the system at just the right frequencies, right? If you perturb the system with a frequency that is proportional to the epicycle frequencies, then you will get a strong and potentially, you'll get a strong response from the system that might actually be a road to chaos. So here we're going to show an example of what I mean by resonance, right? But this is a resonance that doesn't actually cause chaos. This is actually a resonance that will stabilize things. So this is what's known as resonant trapping for the Lagrange points. So this is a very limited version of the three-body problem. We have the sun, we have the Earth, and we're going to explore what happens to small objects as they orbit around in this potential, right? So it's not a full three-body problem, because the little objects we're going to place around here, they're too small to have any influences on the sun or the Earth, right? But nevertheless, it's already a markedly more complicated problem than just the Kepler thing, right? And what we're doing is here we're placing ourselves in a frame of reference where both the Earth and the sun are fixed, right? So you can imagine that actually, obviously this system is rotating, this reference frame is rotating over a year, right? It takes 365 days for the Earth to come back. So in reality, we have a rotating reference frame, but we're going to freeze it, right? We're going to say no, but we're going to say we'll take the reference frame where both the Earth and the sun are fixed. And in this reference frame, therefore, any point that seems fixed actually has a centrifugal force, right? So you know, you all know that, you know, if you're in a car and you swerve left, for instance, well, you're in a reference frame where the car doesn't move, right? You're in the fixed reference frame of the car. So when you swerve left, you feel a centrifugal force towards the right. Well, the same thing happens when you're in the rotating reference frame of the Earth. Basically, the Earth seems fixed because it's as if it was both attracted by the sun and repelled by centrifugal forces. And these two things compensate themselves exactly. And so the question is now, what happens to different points? Like, what is the influence of the sun's gravitational force, the Earth's gravitational force, and the centrifugal force on any point in this space, right? The things that you see, these lines, they're known as equipotentials. So they're kind of like, so you remember if we model a potential as a kind of valley or a hill. So imagine this is potential energy, this is x. So we saw a whole bunch of potentials that, you know, for instance, look like this. Well, these lines, they describe lines of constant energy, of constant potential energy. So it's, imagine, you know, if you were to, you know, if you've ever seen, you know, maps, like walking maps, what are they called? You know, maps with the contour lines of the height, right? The word in English escapes me. But you know, if you look at a map of a mountain, usually what's shown is you have contours of equal height. Well, this is basically what this is, but for equal potential. So for instance, if this thing were a 3D thing, then you could imagine that the lines would do something like that. You'd get a point here, you'd get a line here, a line here, and a line here, right? And so on the other side. Like that. Okay, so these things, they're a way of tracing the hills and valleys of your potential, right? And if you do that, you realize that there are actually 5 points which are of notable interest. So these 5 points, they're called the Lagrange points, and they're actually the points where you have a precise compensation between the influence of the Earth's gravity field, the sun's gravity field, and the centrifugal force, which pushes things away towards the outer space there. So what that means is that if you rotate with the same period as the Earth, and you're located on L4, for instance, you won't actually feel any net force from the system, which means that you won't move, basically. Any point, any object that is moving around on a circular orbit with a 365-day period will remain there. It's actually going to be trapped here. And this thing is known as resonant trapping, because basically it only works if you're going at the same, if you're circling with the same period as the reference frame itself, right? So the Earth moves around 365 days, so if you want to stay on this point, you need to be on a 365-day period as well. So these things, they have a bunch of applications. So if you want, for instance, if you want to send a satellite that always remains with its back to the sun, and where it's always in the Earth's shadow, you can put it on L2, right? We put lots of satellites on L2 because the Earth is always blocking the sun's light, and this point is stable. So once you're on L2, you just shut down the engines, and you're just going to stay here forever, right? So for instance, we put the Gaia satellite, which is an observatory for the Galaxies, over there on L2. There are also more kind of other applications, which are that we know that there were what's known as Trojan asteroids, which are asteroids that actually get trapped around these points. So if you look around L4 and L5, you'll see a whole bunch of small objects that just had the misfortune of being trapped in the valleys, right, of this potential, and they just remain there, right? So they're rotating with the Earth at the same rate as the Earth, and they're staying on L4 and L5. So okay, so we've seen this is what's known as time-dependent perturbation, right? But now. And now we've seen how it can actually lead to stabilizing a system, right? That's the first thing. But it also can have destabilizing influences. So this is a problem that's known as the Kirkwood gaps. So back in the late 19th century, a guy named Kirkwood from America realized that actually when he was looking at the distribution of asteroids in the solar system, that they weren't actually distributed in a neat kind of in a neat homogeneous way. That they really formed. They had you had large numbers on these rings, and then you had gaps, and then another ring, and another gap, and another ring. And so he wondered why that might be the case, right? Why is it that you get this ring structure, right? And he realized that in order to explain that, what you had to do was look at how these things were rotating with respect to Jupiter, basically. Because again, if you simply model the solar system as just the influence of the sun, which is true to a certain degree, right? But once so the sun itself takes care of 90% of your problems, right? Just the presence of the sun is really the main influence in the solar system for obvious reasons. But it wouldn't explain this gap structure. If only the sun were important, then you'd expect these asteroids to be, more or less homogeneously filling a certain region of space. But that's not actually the case. What is the case is that you have these gaps in the structure. And what Kirkwood realized was that if you plotted the number of asteroids as a function of the distance to the sun, that really had this structure, right? And that these things, these dotted lines where you have no, no asteroids, they correspond to orbital resonances with the motion of Jupiter. What does this mean? So, for instance, you'll have the 2-1 resonance over here. The 2-1 resonance means that the asteroid is going around the sun twice as fast as Jupiter, which means that Jupiter is actually meeting the asteroids at very similar points in their period, right? So for instance, if one of the asteroids goes like this, so it's gone around twice, and Jupiter is back here. So every 2 years, every 2 Jupiter years, right, they'll encounter each other at precisely the same point in the asteroid's motion around the sun. This actually it should put you in mind of a kind of resonance that right? It's a swing. What drives a swing is that you push the child on the swing at a regular rate every time at the same point of its upswing or its downswing, right? It doesn't work if you push at different, if you randomly push at different points in the swing, then you're not really going to observe much oscillation. But if you push at just the right times, so for instance, if you push the child every time he comes back up, that's a 1-1 resonance. If you push him every other time he comes back up, that's a 2-1 resonance. If you push him every third time he comes back up, that's a 3-1 resonance. If you wait, if you have a ratio of 5 to 2, meaning the child goes around 5 times and you've pushed him 2 times over this thing, there's a 5-2 resonance, etc., etc. Basically, you can have all kinds of ratios between the period of the child's swing and the period at which you push it, and that's very analogous to what's happening here. Here, Jupiter's pushing the asteroids at a regular interval, right? Every time one of the asteroids back here, so every 2 Jupiter years, the Jupiter is coming to push the asteroid. That's the 2-1 resonance, etc., etc. And these things mean that any orbit, any asteroid that actually lies on these resonances is going to feel the influence of Jupiter very strongly, right? And what that's going to mean is that the orbit is going to increase in amplitude, right? Basically Jupiter is giving energy to these asteroids in the same way that you're giving energy to the child on the swing, which means that these orbits are unstable, basically. The orbits, the asteroids can't stay there because as soon as they get to the resonant points, they get driven by Jupiter until eventually they have enough energy to just leave the gap, basically. So they leave the zone of the resonance and they move either towards here or towards here. Which is why they're all clustered away from the resonances, right? So here, the interesting thing is that none of these orbits here are chaotic, right? These orbits, the orbits of the asteroids themselves are regular, but the reason they're regular but have this weird ring structure is that actually the orbits would become chaotic if they lived in these gaps, right? These gaps make the motion unstable. Oh, also, I don't know if you can see the green here very clearly, but these two green things, they're the Trojans and wait, what are they called? The other Greeks. Yeah, the Greeks actually they're called. So Trojans and Greeks, and if you'll notice, these green things, they pretty much lie on L4 and L5, but of the Jupiter Sun system instead of the Earth Sun system. So essentially, these guys, they stick around here because they're trapped at the Lagrange point resonance, the co-rotation resonance. Okay, so this is the first domain of application, right? You can see what resonance means is that if your system has a particular frequency with which it repeats its own behavior, then if you push that system around that frequency, you will get maximal response from it, and as a result, you might actually prevent the system from settling in certain regions of its phase space. Pardon? Oh, no, beyond these circles, that's just this, basically you have other asteroid belts, but they're much further away. It's just that these, actually I don't know exactly why this, how this asteroid belt formed. I can't remember exactly. But essentially, yeah, it's just that initially you could imagine that there was one belt and all the gaps here were cleared by Jupiter. But over here, that's just that there are no asteroids. It's not a resonance or anything. Okay. So another beautiful example of this are the rings of Saturn, right? So the rings of Saturn, as you all know, they have gaps. They're not actually smooth and anyway. And you might ask yourself, well, why are there gaps in the rings of Saturn, right? This is kind of a salient trait of Saturn's rings, and basically. The way to think about it is to basically know how they were formed, right? So how a ring forms, usually, is that you have some kind of like small moon that'll arrive next to Saturn. But Saturn is so massive that if you approach it too much, the tidal forces from Saturn will just break the satellite apart, right? So you reach Saturn, you break, and your material gets scattered over the ring. So that explains the formation of the ring itself. It doesn't explain why there are gaps. The gaps, well, if you remember the Kirkwood gaps, you probably have some idea, which is that it's probably a resonance, right? There's something, something is pushing these little bits of rock and ice, so this little debris of the disrupted satellites. Something must be pushing them at some kind of resonant frequency in order to clear these gaps in the ring system. And as it turns out, that's exactly what's happening, right? That was a hypothesis that was put forward by Tremaine in the 70s, which is that actually there are things that are known as shepherd moons. So basically Saturn has a bunch of moons, and some of these moons enter in resonance with some of with material in the rings and can affect them in such a way that it clears these gaps in the rings. So here's an example of an animation that shows this. So these are actually pictures, I think, from Cassini. I'm not entirely sure. It's from the NASA website. That's probably Cassini. So here, this is Prometheus. So Prometheus is one of Saturn's moons. This one, I can't remember what it's called. Pandora, apparently. So what you see is that as soon as Prometheus passes round, it leaves this kind of wake behind it, right? And the thing is that this wake acts in such a way that essentially if you're around here, if you were in the gap initially, you're going to feel this force with regularity, and you will get pushed either to the left or to the right. Basically, you're not going to be able to stay in the gap because being in this gap would mean that you felt the influence of Prometheus at just the right frequency to drive the response of the system maximally, right? So this is another example of resonance with the same kind of gap structure, except that now here you can see exactly what's happening, right? Because this is happening over a system that we can observe directly. So that's a shepherd moon, as it's called. Okay. So we've seen Saturn, we've seen some asteroids. These are all more or less the same kind of issues. So basically, resonance that's clearing some bits of the phase space. So this is just a zoom on the rings. And now we can think about that question that we asked very early on in the course, right? Is that, okay, so we've seen that chaos can destabilize certain types of systems. We've seen that the three-body system is certainly completely unstable. But what about the solar system as a whole, right? Because it seems, as far as we know, it's been fairly stable, right? No observer, no astronomer over the last few thousand years has observed any kind of shift in the motion of the planets, right? But there are still a few odd things about the history of the solar system that we wanted to understand, right? Notably, there's something known as the late heavy bombardment, where a few 100 million years ago, suddenly everywhere in the solar system seems to have been just bombarded with massive asteroids. And for a while, no one really had a satisfying explanation as to why, right? Until a bunch of guys from Nice came up with this model called the Nice model. So it's not the nice model, it's a Nice model. So the Nice model, what it says is that let's imagine that at some point in the solar system's history, there was a resonance between the orbits of Jupiter and Saturn. So Jupiter and Saturn start to move around each other, but where basically I think it's a 3-2 resonance. I'm not entirely sure. So every time Saturn goes around 3 times around the Sun, Jupiter goes around 2. Which means that at regular intervals, and always in the same phase of its rotation, Saturn and Jupiter are going to be quite close, and they're going to influence each other. So the idea was that this resonance between Jupiter and Saturn could have potentially destabilized the orbits of other planets, notably Neptune, and as a result of this destabilization, a bunch of asteroids that were outside the solar system in the Kuiper belt, they got kicked out, right? Suddenly the system became chaotic, and all of these asteroids just started to scatter around, and that was the cause for the late heavy bombardment. You can have a quick look at at a simulation of this here. So unfortunately, I couldn't find a very good simulation in that. This is the official Nice model thing, I think, and unfortunately, they seem to have. They seem not to have simulated the most interesting frames. So you'll see when we reach the interesting part, it's just going to be like 4 frames, which is unfortunate. But still, you can kind of see what's happening. Okay, so these are asteroids in the Kuiper belt. This is the Sun, and this is Jupiter, Saturn, Neptune, Uranus. We're not modeling the smaller planets because they don't matter here. So as you can see, the orbits do shift around a little bit, right? So it's reasonably stable, but the presence of the other planets, in particular the presence of a big planet like Jupiter, it will actually influence the orbits of Neptune and Uranus, right? But it's fairly predictable, right? You can see here Jupiter vibrating a little bit, Neptune vibrating a little bit along its orbit, but then suddenly, boom, something weird happens. So let's have another look at this, right? What's happening here? Basically, at some point you have a resonance between Jupiter and Saturn, which means that things start oscillating. So you can see the shifts here become a little bit wider, and then at some point it just blows up, right? And eventually what's happened is that as this resonance took place, basically the orbits of Neptune and Uranus were just pushed out to their present positions, basically, and stuff in the Kuiper belt just gets ejected everywhere, right? So this is typical of a kind of instability in a time-dependent in a system that is perturbed in a time-dependent way, right? Where the fact that you're pushing the system at its resonant frequency means that at some point a small perturbation can grow and grow and grow until it's large enough to disrupt the entire system. And then you kind of just kick out all these asteroids, and they go and bombard the Earth and Moon. Okay. So here these were all examples of resonant motion inducing like instability and sometimes something that looks like chaos in the solar system. Now we're going to have a look at a different type of system, namely at stars themselves. Because if you recall, we started this discussion with the quote from Shakespeare, right? So Shakespeare was saying about how he was, as constant as the northern star, and we saw that actually, the northern star isn't constant, right? Its luminosity keeps increasing and decreasing for some reason, right? And what we'll see is that most stars which have variability, they do vary in this very periodic, predictable way, but some stars can actually behave in a slightly chaotic way. So first, what we're going to have to do is have a look at how we model a star in equilibrium, right? This is always the procedure in physics, right? You start out with a simple equilibrium model, then you try and see what happens when you sort of bump it a bit. So the first thing is, if you have a star, the way that it's kept stable is through something known as hydrostatic equilibrium. So what hydrostatic equilibrium means is just that the star is fusing hydrogen into helium at its core. So it's pushing away, so it's heating up gas. That gas, as it's being heated, increases its pressure. So the increase in pressure just pushes the outer layers of the star outwards. But the fact is that this pressure is compensated by the star's own gravity, basically. The star is heavy, so it tends to attract the outer layers to come back towards the center. So you can imagine that if I were to model a layer of the fluid around a star, so this is what a shell around the star's envelope. For instance, I've modeled, I don't know, this bit. So I'm modeling a shell, and this shell is going to be attracted towards the center by a gravitational force, and it's going to be repelled towards the exterior by the pressure forces, right? The pressure gradient repels it over here. And our basic assumption about stars is that they're mostly stable, right? They mostly don't blow up, right? So we know that we have to be at least not too far from hydrostatic equilibrium. So this is the first model, is that we say, okay, let's imagine the stars are in fact perfectly at equilibrium. So the gravitational forces exactly compensate the pressure forces, everything's nice and stable, right? Now, imagine for some reason, so there are a whole bunch of mechanisms within the envelope that allow some bits of the envelope to be pushed outwards a little bit, right? So what happens if I take this layer and I push it outwards a little bit? Well, the gravitational force is going to decrease, but the pressure force is also going to decrease if I go into a cooler region. So if this layer goes into a cooler region, then the pressure diminishes, and so the outward force decreases again, and so I'm going to be brought back. So this is an example of negative feedback, right? Is that the heating up will push the layer away, but as it's being pushed away towards cooler regions of the star, the pressure is going to drop again, and it comes back down. So this is the simplest kind of oscillation a star can have. It's known as a breathing mode. So basically you imagine your nice spherical star, but it keeps going like a little bit like that. Boop, boop, boop. And as it sort of like breathes, well, it will cool down a little bit, or the outer layers will cool down a little bit, reheat, cool down, reheat. And this translates as a variability in the luminosity of the star. So when we saw the North Star, Polaris really does that, right? Basically, every 4 days or so, it just squishes itself a little bit and then re-expands a little bit. So every 4 days or so, it heats up and cools down, which means that its magnitude, so its luminosity, will vary periodically. And that's very regular motion, right? This is, again, completely linear, completely well-behaved. This is the first kind of, usually it's the first model that you have after equilibrium, right? So the first thing is you assume the star doesn't move at all, then you add the breathing mode, so it can just go up and down like that. That's actually just a simple harmonic oscillator, right? What's happening to this layer of fluid is exactly what's happening to a harmonic oscillator which gets trapped around here, right? This layer is going to move up and down around equilibrium. So as you can see, harmonic oscillators are really everywhere in physics. Yeah?
You said the stars are relatively stable structures.
Yeah.
Then why do we need negative feedback in stabilizing?
Oh, but this is the thing. That's negative feedback is why they're stable, right? Because essentially, if you didn't have negative feedback, any small perturbation would be able to disrupt the equilibrium of the star. But the idea is that if you try to push out this layer, it will actually come back because exploring cooler regions will mean that the pressure gradient diminishes, and so you're going to be brought back. There are certain cases where these feedback mechanisms no longer work. Some stars will develop fairly catastrophic instabilities, especially very, very bright stars. At some point they will just eject their envelope, right? So very young, very bright, very hot stars, they have a very short lifespan because at some point they just eject all the stuff in their envelope. But for stars like the sun, for instance, they're reasonably stable. You can see these sort of like breathing modes, right? Polaris is not quite like the sun. Polaris actually has these fairly large breathing modes because it's a fairly bright star, so a fairly young one as well. Okay, so that was the first kind of perturbation we add, right? So at first, stable sphere, then we just kind of like allow for simple harmonic motion. That's just the breathing mode that we saw in Polaris. But now we can imagine, well, if this sphere, it's not a solid sphere, right, the sun, or any star. Stars are made of gas, right? So you can imagine that, sound waves can propagate within the envelope of the star. And also, kind of like what we saw with the Lorentz model, there's a buoyancy, right, in that these bits are hotter than these bits, so you can have lumps of fluid just rising up from the inner layers to the outer layers and cooling down, and basically putting convection in motion. So these two mechanisms, right, on the one hand, the buoyancy in the hotter regions making the fluid move up and down, and also sometimes the sound waves, the pressure waves within the envelope that'll just bounce around the star. These actually give you all kinds of complicated oscillations, right? So now the envelope of the star is not just moving in and out like that, it keeps getting perturbed by all kinds of little waves bouncing up and down the envelope. So these are different modes. For instance, you can see, you can imagine this is a pressure mode. So it's a sound wave that's traveling through the star, and as it enters the more dense regions, it bounces back, kind of the same way as an echo, right? If you shout near a wall, the wall just sends back the sound wave towards you. While the denser regions of the star will act kind of like a wall, right? So you have these pressure waves being sent towards the core, bouncing back here, and just moving around the star. So these are symmetry modes. They kind of work a little bit like earthquakes on Earth. So they're actually called, so this field, the field that studies these things, is called astroseismology, right? So astroseismology is the study of how stars are not in fact completely stable. They have all kinds of little movements all the time. So this was first studied in the sun, for obvious reasons. It's quite close. But we realized that actually we can observe these things in other stars, right? In stars that are quite far away. And this is very useful in order to understand for instance, what the temperature or the size of a very far away star is, right? Because often we have no way to know. So, essentially, we've now made our model a little bit more complex, right? Now this is not even modeled by simple harmonic motion. This can be potentially a nonlinear oscillator. Once we've added this complexity, we can start having the possibility of chaos. And indeed, it seems to have been observed, right? So this is an example of this is a type of variable star, right? So, but this one's not as neat as the Cepheid, it's not as neat as Polaris. This one, it has all kinds of weird noise, right, in the oscillations of its luminosity. And the reason it has the oscillations in the luminosity of this star are not as neat as with Polaris, is that there isn't actually just one oscillation, right? There's a fundamental mode, there's an overtone mode, so another oscillation that happens on a different time scale, and a whole bunch ad infinitum, right? You remember this is like, this is possibly puts you in mind of our old friend Fourier analysis, right? It's like you remember if you're, so you have some kind of complicated looking wave that goes like this. So you have a wave here that goes to this time, this is the amplitude of the wave. And you remember this doesn't look like a neat sine wave, but it can be modeled as the sum of different sine waves. So you say that essentially it's as if you added up sine waves of different frequencies, where this is the fundamental, and then you'll have a few other modes if you to add. You can do exactly the same kind of analysis with the luminosity, with the light curves of these variable stars. What you do is you try and see, okay, how many modes do I need to add up to get the correct change in luminosity with time? And when you do that, you create just a Fourier spectrum in the same way that we did with the electronic signals last week. And you do indeed see that certain stars, they actually seem to have some kind of chaotic component of their oscillation. You remember the way chaos shows up in these spectra is in the fact that you have a whole bunch of noise, right? So instead of having neat peaks at the frequencies of oscillation, as if you had, which is the case when you have a neat oscillation like that, well, if you add up a whole bunch of stuff that goes like that, so just noise, this stuff is a sign that you have chaos, right? Because now your system isn't just oscillating at regular periods, it's oscillating at all kinds of different periods and no longer really showing any kind of pattern, right, in its movement. So this is what happens. So you take one of these variable stars, so these ones are called delta Scuti, and what you do is you take the spectrum of oscillations in luminosity, right? You take the spectrum, and at first, so this is the actual spectrum, right? So this is the amplitude, this is the spectrum, this is the frequency going from left to right, increasing from left to right. So what you see is that the broad stuff, so the main features are very much not chaotic, right? So you have very clear fundamentals and overtones, right? So you have a few frequencies which really dominate the spectrum completely, right? So this kind of imagine like this. In this system here, these two frequencies really dominate, right? But once you get rid of these frequencies, so here in this plot, we've removed the 50 largest peaks, so we can zoom in on the bottom here. And we look at the bottom, it's got a whole bunch of noise, basically. It's got a whole bunch of, the spectrum over here, so this fairly low frequency spectrum, is actually continuous, right? It no longer has neat, well-defined peaks, it's just white noise, basically. And this tells you that it is at least plausible that there are chaotic modes in the oscillations of these stars. So actually stars can behave under some conditions as chaotic oscillators. So what we've seen so far is chaos can occur in planetary systems. So we saw the resonance and the kicking out of satellites and stuff happening with the Nice model in the solar system. It can also happen in stars themselves. So stars themselves are kind of like, they're oscillators that can potentially display chaotic modes. And now, what we're going to see is chaos in galaxies, right? So galaxies, as you all know, they're just very large collection of stars. A lot of galaxies have, well, galaxies like the Milky Way at least, they're mostly organized around a disk. So you have a big disk of stars and, a whole bunch of other features which we'll talk about. So the question is, okay, so we're physicists, we want to model a galaxy, right? We want to figure out a fairly straightforward procedure to, to capture the basic behavior of stars in the galaxy. So what we're going to do is, first of all, try to describe the potential, well, try to find out what the matter distribution is like, and figure out what kind of potential this drives. Okay, so this is going to, this word potential, I think I'm going to have to explain it a little bit, because it is quite important. But it is something you've already seen, basically. Okay. So, imagine the simplest kind of distribution, right? So this is a point mass. So, imagine, it's not really a galaxy because you imagine that it's as if the entire mass of the galaxy had concentrated to one point at its center, right? So if you have a point mass, then what you know is that the force on any given point around it, so this is the mass m, the force acting on any point around it decreases as the inverse square, right? This is just force, the Newton gravitational force, right? So what you can say, in other words, is that the potential energy of any point around here is decreasing as you move, it's increasing as you move along, right? So what this looks like is that you have a potential energy that goes as, well, it's proportional to 1 over r. So basically it goes something like that, right? So this is the particular, so the idea is that you pick the distribution of matter. In this case, everything's concentrated at the center, and this gives you, how stuff around here will be affected by the presence of the matter. Then, you can actually have another type of distribution, which is the second extreme. So this is called the Kepler potential, actually. The second extreme is, you imagine, instead of having a point mass, we're in a galaxy where mass is uniformly distributed everywhere. So homogeneous mass distribution. So in a homogeneous mass distribution, it's like the density of matter is the same everywhere. So it's just, you imagine, your galaxy doesn't have any particular features, it's just a soup of matter. And in this particular case, the potential that you get, so this is, you imagine this soup of matter here, well, the potential that you get is actually proportional to r squared. So if r is the radius separating, so this is, for instance, so the potential energy is now proportional to r squared. This should actually put you in mind of something. This is just a simple harmonic potential, right? Oh, sorry, also definitely not like that. We want like that. Okay. So here we have, potential energy, and here we have R, and that'll go something like that. So this thing is just something you recognize, right? That's the potential energy for simple harmonic motion, right? So you already have the two extremes of matter distribution in the galaxy. So either everything is sitting at the center, or everything is filling out the space homogeneously. And these give you two different types of potentials. One of them is the Kepler potential, which goes as 1 over r, and the other one is the simple harmonic potential, which goes as r squared. And once you have the potential, what you can do is quite simply, you throw around a bunch of stars in space and you see how the orbits evolve. And this thing, so for the simple harmonic oscillator, it's very simple, right? As you recall, it's just a bunch of circles. If you start out with the potential of you start out with a matter distribution that is homogeneous, so just matter being distributed everywhere evenly, then in that case, the kind of orbits that you'll see will just be the same as in a harmonic oscillator. So there'll be circles in phase space, right? In real space, what it'll look like is something like that. So this is, for instance, what happens if you have something that looks like a harmonic potential. This is what's known as a box orbit. So basically here, this is the center of your galaxy, and what is happening is that you're moving around along this path. So as you can see, this kind of orbit, it's constrained in space, but it goes through the center of the galaxy. The other type of orbit that you're allowed is closer in spirit to the Kepler potential, right? So the Kepler potential was planets orbiting around the sun, for instance, right? Except that here, you're not quite at the Kepler potential, you're at a slightly different potential. So now the star, instead of being able to oscillate across the center of the galaxy, is only able to go around it like that. And basically it does a rosette, right? The same thing that we saw right at the beginning. Now, the problem here is that we want to be able to visualize the phase space of this sort of thing, because ultimately phase space is where interesting things happen, or at least it's where the structure the whole structure of the system is visible. So what we do is you do what's known as a Poincaré section. So this is the Poincaré section. The way it works is quite simple. So you plot one of the components, x, and the speed. So this is the position along x. This is the speed along x. And basically, it's as if you were cutting the orbit here, and you look at where the orbit crosses this particular area, right? So every time the orbit passes here, you mark a point here. You mark a point at its position and with its velocity, right? So this is kind of how you do phase portraits, but except, a phase portrait was useful for a system that was one-dimensional, where you had x and the x, but this system has a position in x, a position in y, and a speed along x, a speed along y. So in order to visualize this, you're going to use this thing called the surface of section. So really just imagine, yeah, I've put a plane like that, and I'm just looking at the position and speed of the star every time it crosses that plane. And what you'll see is that different orbits, different families of orbits will show up differently with different structures on this Poincaré section. For instance, the loop orbits over here, well, they never cross the center, right? So this is the center. At the center, you have 0 velocity, 0 position. So the loop orbits never actually cross this bit. They can only go, they go around like that. So every time they cross, if it's a simple loop, so this one, if it actually closes up on itself, then it shows up on the Poincaré section like this, right? So basically, if you imagine putting a section here, and if you imagine an orbit which is really just a closed loop over here, then it hits the surface, well, this surface here, it hits it once here, and every time with 0 velocity, right? So this here, these are the signatures of the closed orbit on the Poincaré section. The rosettes, they're just going to come up as little circles around it, right? So you can imagine it's like we had this, if you have a torus and you slice through it, so if you slice through this thing, then what's going to happen is that if you have an orbit here, it'll keep crossing your Poincaré section until it traces these two circles over here. On the other hand, orbits that do cross the center, that are allowed near x equals 0, basically what these things do is that they won't stick around here, they'll live in this part of the Poincaré section. So these bits, these surfaces here, the ones that go via the center of the galaxy, these correspond to the box orbits over there. So, none of this is chaotic yet, right? So for the moment, we have a very well-behaved galaxy. Everything, you can imagine that it's more or less what's known as axisymmetric. So it's more or less, a flat disk, which is with no variation, with not too much variation in mass. And the stars, they get the choice. Basically, they can either orbit around like that, around the center, with forming a kind of rosette, so never quite looping back on themselves, or they can orbit like a simple harmonic oscillator, like that, and forming these little loops like that, and forming a box orbit here. We visualize this in phase space in this way, with the Poincaré section. And we can ask ourselves now, okay, so what happens if we change the parameters governing the mass distribution in this galaxy, right? Well, what's going to happen is that, well, first of all, we need to pick a potential, right? So for instance, we can choose this particular potential. So this is the Inl-Hiles model. So you can imagine these are contour lines, right? So every line here represents a region of equal potential energy. Again, imagine this as a sort of, you're trying to plot mountain relief in 2 dimensions, right? So everything here is of the same height. These lines are the same height, and like that. So basically, you have a kind of valley here, hills over there, and you're trying to see how things will move around in this particular, mountainous and valley-filled system. Well, what happens is that you can look at different types of initial conditions. So E here is the energy, is the global energy of the orbits you're sending through this little system of valleys and rifts, which are made to model the potential of the galaxy. And what happens is that at first, at low energies, you have fairly regular motion. Actually, you can see that these things, they kind of look like the loop orbits that we saw, right? So these are the Poincaré sections, and what you get are these circles where each lump here, that corresponds to a particular orbit as it crosses the Poincaré section. And at first, it's all very regular. Then what you start noticing is the appearance of little islands. So basically around here, for instance, as you increase the energy, basically what's happening is that some orbits get trapped around these points, which look a little bit like the Lagrange points, right? It is the same kind of resonant trapping, except we're not looking at a two-body problem, but it's the same kind of idea, right? Like, there are certain bits of the phase space, as you increase the energy, which start trapping orbits around them. And so orbits around here, in these island chains, what they do is that they visit each island separately. As you cross, basically, if you can imagine where we're crossing the Poincare section, so we're crossing it once here, then once here, then once here, then once here. You increase, again, a little bit the strength of the energy, and these island chains start breaking up into smaller island chains. And you have, so this is a little bit difficult to see here, so I've kind of magnified it here. So you have the first island chain here, but these two big island chains, they've now split into a chain that goes around here. So you can see these white dots. That's now that's what used to be this island chain. And around these island chains, there's just a whole bunch of noise, right? And these are the chaotic orbits. So when we're studying the orbits of stars and galaxies, what we're trying to figure out is where are the island chains? So these are still, these are still orbits which have regular motion, but just outside the island chains, you have chaotic motion. And the whole idea is that we want to explain, well, we want to be able to describe how when we change certain parameters in the potential, these island chains start appearing and chaos starts to form around them. But again, as in with chaos in dissipative systems, the whole thing doesn't become chaotic here. It's really, you have islands of order, islands of regular behavior, and around it, a sea of chaos. And so this is something as well which has the same features as the fractals we saw last time, right? Basically, as you increase this number, the energy, what happens is you start seeing island chains within the island chains. So we can't zoom in here, but if we were to zoom in on the edges of these island chains, we'd find that actually these also have island chains within them, et cetera, et cetera. So this route to chaos in Hamiltonian dynamics, this actually goes through resonance. Here what's happening is that these things correspond to orbits which are resonant. Okay, so to sum up, a Hamiltonian system is integrable when you have enough integrals of motion to really confine the behavior of the system to a simple surface, right? Do you remember either torus or a line, something like that. Quite often the system is non-integrable, so we have two options. Either we try to, either we give up, basically, or we model it as the sum of an integrable part and a perturbation. And what we saw is that when we add this perturbation, we can get chaos arising near resonances, right? And this can arrive either in a time-dependent way or in time-independent way. The dynamics on display, we've sort of investigated it in a whole bunch of different types of systems. We saw it in the solar system. We saw in for instance, the distribution of asteroids with the Kirkwood gaps. We also saw it in the stars themselves, right? Chaotic oscillators with the stars. We saw also, we saw briefly the galaxies as well. So what happens when, as you modify the potential of a galaxy, you start getting regions of chaos in the orbits around it. Although I feel like that maybe wasn't the clearest part of my explanation. I think I was kind of losing you there. So I'll try and figure out a way to explain this more clearly, I think, tomorrow. And yeah, that is all for today. So tomorrow what we'll be doing is really looking mostly at some history of chaos. We'll have a look at a few special topics. If you have any suggestions, anything that is of particular interest to you, you should definitely send me an email or come see me in my office in the next couple of hours, where, because the idea is that we should start doing a more kind of like discussion-based class, right? Where you kind of tell me what it is that, what are the concepts that strike you as useful in what we've seen so far. In terms of readings, so this section is a bit odd because basically the introductions to chaos typically don't talk about Hamiltonian systems much. So in the Intro to Chaos by Smith and in the Chaos, the Making of New Science by Gleich, there's hardly anything on Hamiltonian dynamics. The problem is that it's just a little bit mathematical. So if you're very brave and want to actually see the kind of like the mathematical stuff, it's in here. For applications to galactic astronomy, they're in Binion Tremaine, galactic dynamics. Although I think I'll maybe try and find a clearer way to explain some of the stuff that we went through in the last 10 minutes, because I'm not entirely satisfied with that. Okay, do you have any questions? Yeah?
Aren't numbers when you actually talk about chaos in the solar system? I'm not sure that's relevant, but whatever our current predictions are about positions of different planets in the solar system, and because there's chaos there, do you see any kind of changes in those predictions?
So this is the thing, actually, is that it seems that for the moment it's stable. If you remember the little video, most of these changes happen over the course of millions, tens, hundreds of millions of years, right? So as far as we know, at the moment, it's quite stable. But this is the whole thing about chaotic systems, right? Is that they can look pretty stable for a while before starting to do some funny stuff, right? So as far as we know, I think that our best guess now is that it's stable for the moment, probably stable over the medium term, and then different types of simulations give you slightly different possible outcomes. You remember this is one of the things with chaotic systems is that they are quite sensitive to initial conditions, so slightly different simulations will give you slightly different, well, very different scenarios. But certainly the solar system seems to be stable over the, it has been stable over the last few million years, and looks like it's going to remain so for the next few million years.
Just a clarification. You said that there are gravitational resonances, and then there are motivations. And it's the motivations which are actually a root chaos, right? But in case there are, say, very large, very strong gravitational resonances, do they also kind of provide some sort of protection from these motivations, which may not then lead to chaos?
So the perturbations themselves don't necessarily lead to chaos, right? You need certain conditions, basically, because usually the assumption, if you're looking at systems which are not too far from equilibrium, the assumption is that mostly their behavior is kind of regular, and so the perturbations can't be huge, right? So these are little perturbations, right? And the idea is, the whole study of Hamiltonian mechanics is to say, okay, well, under what circumstances do these small perturbations become large, right? At what point are they no longer linear perturbations? At what point do we need to take into account the fact that, and the answer to that is at the resonances, right? Resonances are the point at which even a tiny nudge, if it's regular enough, at the resonant frequency, will give dramatic behavior. Again, think of a child on a swing, right? It's like, if you push the child even slightly, at the resonant frequency, and you do it long enough, then eventually you will get some fairly large oscillations, right? Despite your perturbation at any given point being very small. So that's really the link between resonance and chaos, is that resonance is the thing that allows you to explore the kind of nonlinear part of your behavior.